Hey, welcome to video number 2. In this video, we're going to work on pages 2 and 3 of our notes, and that's going to finish out section 2.1. I'm talking about limits. So this is the page in your notes you should be on. So if you'll just find that, let me just check my pen looks good. Okay, the top part is the important part of this section that we're going to work on. There's a relationship between one-sided and two-sided limits. This is a two-sided limit. It's not just considering the left and right, it's looking at both. So this is a two-sided limit. This is a one-sided limit. Do you see that? It's coming from the left-hand side, so we would just take a look at the limit from the left. And this is a right-handed limit. In order for a two-sided limit to exist, the limit from the left has got to equal the limit from the right. If the limit from the left does not equal the limit from the right, then the two-sided limit does not exist. So let's take a look at some examples. This right here is called a integer or a step function. Some people call it a floor function. And an application of this might be like a parking meter. Obviously not in quadrant 3 here, but in quadrant 1, this could represent a step function. So for example, for the first hour you park somewhere, it's free. Okay, that never happens, but let's pretend. Then from the second hour costs $1. The next hour it costs $2. The next 3 and 4. So that works like with a parking meter or in a parking garage. You don't pay incrementally for the minutes, you pay by the hour. So if you had stayed for 1 hour and 59 minutes, you would still only pay $1. If you had stayed for 1 hour and 1 minute, you would pay $1. So that's an application of this kind of function. Like taxes are also formulated this way. You pay a certain percentage of tax until you're in a different tax bracket. So that's what these kind of functions represent in the real world. But let's take a look at this situation. The limit as x approaches 2 from the positive side. So here's x equals 2. Coming at this from the positive side, that equals 2. Okay, coming at this from the negative side, from the left-hand side, that's going to equal, oops, I'm up here, excuse me, that's going to equal 1. So the limit from the left is not equal to the limit from the right, so therefore the limit at 2 does not exist. So we're going to kind of cheat and do that abbreviation for does not exist. But f of 2 is actually equal to 1. So it is defined at 1. Okay, go ahead and hit pause, and I want you to try this set of questions here about the limits as x approaches -3 and the value at -3. So these are the one-sided limits, that's the two-sided limits. So hit pause and give that a shot, and then we'll check your answer. Okay, did you really hit pause or are you just faking it? All right, either way, here we go. So the limit as x approaches -3 is going to be -3 from the left-hand side, or the right-hand side, excuse me. So as we approach -3 from the right-hand side, that's going to be -3. As we approach from the left-hand side, that's going to be a -4. And the limit as x approaches -3, the two-sided limit, is non-existent, does not exist, because the left-handed limit does not equal the right-handed limit. But f of -3 is actually going to be -3. Okay, let's try another example. This is just a piecewise function. The limit as x approaches -4 from the positive side. So that looks to me like it's going to be 2. The limit as x approaches -4 from the left-hand side, the negative side, is also equal to 2. And here the limit, therefore, from the left and right are the same. So therefore the two-sided limit is equal to 2. Now g of -4, if we look, it's undefined. It's not defined in this piecewise function, so we're going to write does not exist. Okay, go ahead and pause it, and I want you to try this set of problems and this set of problems on your own. Then I'll show you the answers and we can compare. Oops, I'm getting stalked by HP Instant Ink. I know I'm out of ink. Okay, sorry about that. So go ahead and solve these two, hit pause, and then we'll come back and take a look at the answers. Okay, so hopefully you've hit pause and you've practiced those. So this here is going to be a -2. This is a 4. The limit obviously does not exist because left and right hand limits are not the same. And g of 1 is equal to 4. And then for this problem right here, as we approach 6 from the right hand side, we get a 5. From the left hand side, we get a 5. The limit, therefore, is equal to 5. The right hand and the left hand limits are the same. And g of 6 is actually down here, and it equals 2. Okay, so that's how you do right-handed limits, left-handed limits, and two-sided limits. And the important thing to remember is if the right-handed limit and the left-handed limit are not equal, then the limit does not exist. Okay, moving on. I've listed for you in your notes properties of limits. You can multiply a limit by a number. You can add limits, subtract limits, multiply limits. You can divide limits as long as the limit of g of x at a is not equal to 0. And then you can also take a number times the absolute value of a limit. So there's just a set of properties for limits that have been spelled out for you. Okay, next. So strategies for finding limits, graphs and tables, we have already worked problems like those. So those have been given in examples above. But if you don't have a graph or a table, the easiest approach for limits is just to substitute the value to see if you get a number. So let's go ahead and substitute 1 in for x. So we're going to get a 1 squared plus 1 plus 2 all over 1 plus 1. So that looks to me to be 4 divided by 2, which equals 2. So this limit is equal to 2. Okay, let's look at example 2. What do you think the graph of pi cubed looks like? Well, pi is 3.14-ish. Cubed would be maybe about 27, a little over 27. So this would be a horizontal line at 27. So the limit of a horizontal line at 0, so if you can kind of imagine this, let's say this here is 27. This function would be right above it. This is obviously not to scale. So the limit as x approaches 0 would just equal pi over pi cubed. Okay, and then let's go ahead and do substitution with this limit. That would equal pi times cosine pi. It's really important that you are good with your unit circle. So if you're not, you might want to print off a copy, have it handy, and practice memorizing it. So here we are at 0, here we are at pi. The values at pi are -1, 0. And cosine of pi is -1, so that's going to equal -1 times pi, or negative pi. So you can always substitute a value. So that's one way to find a limit. Okay, let's flip to the next page. Another strategy is factoring. So if we substitute -3 in here, we're going to get -3 in the denominator. I'm sorry, we're going to get -3 plus 3 is going to be 0, and we get 0 in the denominator, and that's undefined. So in this case, we can't substitute. So what we can do is try to simplify. So the limit as x approaches -3. All right, let's factor this. So I think that's x plus 3, x minus 2. So I'm going to factor my numerator. And nicely enough, those x plus 3's cancel. Graphically, it's going to look like a hole. Okay? So now, because these two factors divide to 1 or cancel, I can sub in a -3. So then I get a -3 minus 2, which equals -5. So this limit is equal to -5. Okay, we can try this again here. This is actually the difference of cubes, and I don't know if you remember this pattern or not. It shows up occasionally. So a cubed minus b cubed is equal to a minus b times a squared plus, that's the weird part, right? ab plus b squared. So that's the pattern. The sum of cubes, if you want to jot that down, a cubed plus b cubed is equal to, sorry, my pen's kind of slow, a plus b times a squared, can you guess what's next? Minus ab plus b squared. So that's the sum and difference of cubes. Okay. So we're going to do the difference of cubes. So our a is equal to x and our b is equal to 1. So this is going to equal the limit as x approaches 1. And our numerator is going to be x minus 1 times a squared, so that would be x squared, times, remember x is, or a is x and b is 1, so x times 1 is just x, plus b squared, b is 1, 1 squared is 1. So it's important to know that in this pattern, b is 1. b is not -1 because the pattern is a cubed subtract b cubed. So a is x and b is positive 1. Over x minus 1, the x minus 1's now cancel. And now I can substitute. So that becomes 1 squared plus 1 plus 1, which would equal 3. Okay, so factoring is another strategy. So to sum it up, we can look at a graph and see the limit from a graph. We can make a table, which we made on the very first page of our notes. We can substitute the value to see what we get. We can try to rewrite the function, and factoring is a common way to do that. So adding on to those strategies are the squeeze theorem. This theorem is when we squeeze our function in between two simpler or functions that are more known to us. So if I look at this right here, we're going to prove that this limit equals 0. So what I'm going to do is I'm going to start by, I'm going to get my calculator, and I'm going to graph x squared times sine of 1 over x. So I'm going to add a graph. Okay, so I'm going to do x squared. Sorry. You know I have summer brain, so it's hard. Anyone else struggling with that? Okay, x squared times, we're going to do sine of 1 over x. I hope you're all following along with me in your calculator. I know it might seem silly, like you could just watch me do it, but you need to be really fast with your calculator, and the only way to do that is to practice. So I'm going to encourage you to use your calculator along with me so you can just practice. Okay, I'm kind of curious what's going on right here because I want to know the limit. So I'm going to adjust my graph, and I might go to Window and Windows Settings because I like to micromanage and pick my Windows settings. So I might make this a -1 and this a 1 and do that with my y value. I really kind of want to just zoom in and see what's happening there. Whoops. Oh geez, I should have left it highlighted, sorry. Okay, -1. And then, let me try to be more efficient here. 1, better, okay. So I'm going to zoom in and just see what's happening. Well, it's still hard to see, right? Okay, so what I'm going to do is I'm going to squeeze this function in between two functions that I know. And I'm going to use this function right here because I know what that looks like. That's an easy function to work with. So on the Inspire, you're going to hit Tab to make a new line. So I'm going to do x squared. And that's going to be like my upper boundary. And then I'm going to do negative x squared. And that's going to make my lower boundary. So I might zoom out a little bit just to make sure that this really does. Do number 4. Whoops. Menu. Number 4. I'm going to zoom out. And I want to zoom out with my center beam here. I might zoom out a little bit more even. And if you can see, in fact, this blue function, which is my sine, my x squared times sine of 1 over x, is in fact in between these two functions. So it's like we've squeezed this blue function inside of the red and the black function. Okay, so I'm going to go back to my notes and we're going to draw this. Oh my gosh, seriously, I'm being stalked by HP. Okay, I've got to fix that setting or go buy some ink. Okay, so this is what it looks like. So this is our x squared. And this is our negative x squared. And this is our, I might make it red. I'm going to make our other function red on here. It kind of does something weird, doesn't it? Kind of goes up, and then it does something weird, and then it goes down, and then like this. All right, so we've squeezed this function right here in between two functions that we know pretty well. So negative x squared we've established is less than x squared times sine of 1 over x, which is less than positive x squared. So if we know that the limits are equal to 0, so the limit as x approaches 0 of x squared is equal to 0. So we know, let's write that out. So we know that the limit as x approaches 0 of negative x squared is equal to 0. And we know that the limit as x approaches positive x squared is equal to 0. So if this limit is equal to 0, then this limit is equal to 0. Then we know that since this is in between, then therefore this is also equals to 0. So therefore, by the squeeze theorem, I think I lost an E there. The limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. And you might be saying to yourself, how did you know to use x squared? Well, usually it's going to be a function where there's one component of the function that you know, and that's the component that we knew. And with practice, you'll get it. And it's pretty, it doesn't show up a ton, but you'll get the hang of it. Squeeze theorem. Okay, and then finally, this last part for today, limits that fail to exist. So we're going to use our calculator to help us. So we're going to take a look at this function, absolute value of x over x. So going back to my calculator, I'm going to make a new page. And I'm going to add a graph. Okay, so I'm going to do fraction bar. The absolute value on the Inspire is, see this bracket button right here? If you hit that, you'll get absolute value, and it's right here. So let's see if I narrow over. Oh, geez. There we go. I'm struggling with using this with the computer, so I'm sorry. Okay, let's try again. Control, brackets, enter, absolute value of x, and we're going to divide that by x. And let's take a look at that. Okay, so we see the limit as x approaches 0 is going to be 1 from the right and -1 for the left. So based on our definition we explored earlier, that limit does not exist. So let's just make a sketch of that graph so we can have that example. Whoops. So here's 1 and -1. And it's undefined at 0, right? So really, there would be an open circle here and an open circle here. So this limit does not exist. Okay? All right, let's take a look at 1 over x squared. I think I know what that looks like, but let's go ahead and just verify. Make a new page. All right. So 1 divided by x squared. On the Inspire, you do have to hit enter. Okay, so that's what that graph looks like. So if I look at that, as x approaches 0, that's going to positive infinity on the right, positive infinity on the left, and therefore that does not exist. Even though they're both going to positive infinity, infinity is not a number. So you never really get anywhere. So that's going to be, it's unbounded, meaning it goes on forever. So therefore that limit does not exist. Okay, and then the last limit that does not exist is we're going to look at oscillating behavior. Oscillating is an up-down behavior. So let's do sine of 1 over x. You could do graphs one on top of each other if you are using your own calculator, but just so it's not confusing, I'm going to make new pages, but you don't have to. Okay, sine of 1 over x. Let's take a look at that. And if we can zoom in on this right here, so I'll do menu. Oops, number 4. Oh, I don't know what I had. Okay, menu. Let me try again. Oh, geez. Menu. Zoom in. I don't want trace. Okay. I obviously need to practice. But if you look at this, it's going up, down, up, down, up, down right here around x equals 0. And that's oscillating behavior. So it's never actually going to approach a value. So I do really want to show you that. So let me try it again. Number 4, number 3. I'll make this the center. There we go. That's cooperating a little better. And as we zoom in, do you see how it's going, even though we're zooming in like with a microscope, getting closer and closer, we can see that oscillating behavior, that it's just going up, down, up, down, up, down, and therefore it's never approaching a value. So that is oscillating behavior, and that limit does not exist. So we could draw that, and I'm not sure how it went, but then it goes crazy. Something like that. And that does not exist. Okay, thanks for hanging with me as I was slow with the calculator, but there you go. There's section 2.1. I'll be posting a couple practice problems for you to work after you've watched these 2 videos. So thank you very much. Hope you guys are having a good day.